Hello again, calculus students. Now's the time where we get into the nitty-gritty of finding the area of functions. And what I mean by that is finding the area of this function underneath this curve and above the x-axis. So that would be this area all in here. Okay? And I'm going to tell you that we're going to find this area by using rectangles. Okay? That is the only way we know how to do it. Now, you can look and say, well, this sort of looks like a trapezoid of some sort, okay? And if you found the area of a trapezoid that had the base and height of this, it would be close to the right area, but not exact. And we're going to be able to use rectangles to find the exact area of this thing. So here's how it's going to work. For instance, what we're going to try and do is we're going to take this space and divide it up into a specific number of rectangles. And for right now, let's say that they all have the same width. Now, they don't always have to have the same width, but they could. My picture's not going to be good here. Let me move B over a little bit. Alright, let's say B is right there. Make my picture nicer. Alright, now essentially the idea is if we added up all the area of these rectangles, it would be an approximation to the total area underneath of the curve. Now, as you can see, it wouldn't be an exact answer because we've got some space right here, 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 and here that we're not accounting for. But for right now, we're just going to disregard that and say that this is a fairly good approximation. Well, here's how we figure out what the area is. We're finding the area and then adding it all together. And so essentially what I'm doing is I'm taking base times height plus base times height plus base times height and so on and adding up all these together. Let's call the width of each of these delta x. And they're all going to be delta x, blah, 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 all the way across. Each width is delta x. Now the height of these is going to change. It's going to change based on how high it takes to go and touch the graph. All right, so it basically is based on the function. All right, let's call each of these, and I'm going to erase this, they're going to be in my way. But just remember, all those are delta x. Delta x is the width of the rectangle. Let's call this x1, x2, x3, x4, x5, and x6. I have 6 rectangles, 1, 2, 3, 4, 5, 6. And in order to find the height of those rectangles, I have to place these x values into my function. That will give me the height. So I'd have the height, the width is delta x, then I'd add them all up. And so the way we write it is like this. Whoops. Let's start with 1. We go to 6. Like this. And essentially what this is doing is it's saying height of the first rectangle by, if we put in 1, that would be the height of the first rectangle because it would be f of 1, times its width, that would give us the area of this rectangle. But we're doing it 6 times. And we're doing it when we use this rectangle, then when we use this one, then this one, then this one, then this one, then this one. And so this sum represents the sum of all of these rectangles' area. And that'll be an approximation of what the area is underneath of that curve. All right, it will look something like f of x1 times delta x plus f of x2 times delta x plus all the way up until f of x6 times delta x. And then all those together give us the total area, just like we said. Okay, well that's nice, that's great, but when we're looking at this, this is an underestimation. We know that we're going to be off because we're missing that area. We could also find an overestimation. And for the overestimation, I'm going to use a different color. I'll use blue. And the overestimation, instead of starting on the left here and going up to touch this, I would start on the right here and having the height be here. And so you can see that these rectangles, when we draw these, are over top of the curve. And when they're over top of the curve, we've got this extra space up here that's too much. And so one of the strategies we have for finding a good approximation is if we take the underestimate and the overestimate and average the two. And let's put in blue overestimate. Now, the average of the two still is not the exact area, and I want to make sure that that's clear. It's still just an approximation, but it's usually a better approximation than just having an overestimate or an underestimate. So, the idea behind integral calculus is that as the number of rectangles increases, the error is going to be smaller. Okay, and if you can imagine that, imagine doubling the number of rectangles here. And before, whereas this area was fairly big in each of these, that area is going to get a little bit smaller because the number of rectangles that we have has just doubled. And so let's say we doubled it again, and then again, and then again, and we just keep doubling the number of rectangles, and we go up and we get to an infinite number of rectangles. Well, when we have that infinite number of rectangles, then the error is going to be non-existent. There will be none, which would give us the perfect area underneath of that curve. And that's how the rectangles are going to be used to find areas of things. All right, we're going to make them infinitely skinny, but adding up all their areas is going to give us the correct area. And that works with any shape and any function. All right, and so chapter 4 is about learning how to do that. You might ask the question, well, Mr. Stencil, if I get an infinite number of rectangles in between here and here, wouldn't that mean there would be no width? And technically, yes. If you have an infinite number of rectangles, it's like each of them have a width of 0, but they don't. And we kind of have to assume that they don't. And that's the assumption that you make when you do calculus, that some things just aren't going to make sense theoretically and physically, but they make sense to us theoretically, and so we can use them. So that's the end of this video. In the next video, we're going to go through some examples of how to actually do this and see where it's applicable. So I will see you in a minute.